Now we're going to do a little conversation, a couple of problems with Kirchhoff's laws, and the thing that makes Kirchhoff's laws difficult is the math, not the physics of it. The math or the Kirchhoff's laws themselves are very easy to follow. However, there is one point that you have to look at very carefully, and this is on page 752 of the book. And it basically talks about how to keep the signs correct. And you need to look at this very carefully and make sure you get this straight in your mind. And there are 4 bullet points at the bottom. It's figure 2124, and the 4 bullet points talk about the direction of the current and whether the sign is positive or negative. And this is in a loop calculation. The first of Kirchhoff's laws is that the sum of a amperage that goes into a joint node has to be the same as what comes out. The loop calculation is that if you do a complete loop in a circuit, the sum of the potential differences or voltages has to equal 0. Well, in order to make sure it equals 0, you have to show or make sure you get the signs correct. And if you go across a resistance in the direction that the current is supposed to be going, then the sign of the I times R for the voltage is negative. If you go opposite of the direction that the current is supposed to be going, then the sign will be positive. If you go from negative to positive in a battery or an EMF source, from negative to positive, which is the same direction that the charge would be moving, then the potential in that battery is a positive. If, on the other hand, you go from positive to negative, which is the opposite direction, then the change in potential or the EMF is negative. You need to study that very carefully as you do these Kirchhoff's problems. Now the first question is, apply the loop rule to A, B, C, D, E, F, G, H, A in figure 2125. Well, A, B, C, D, if you look at figure 2125 and you go around just as it says, this is number 32, so then you start out with I1 times R1. Now make sure you're looking at that figure. I2, R2. I'm just putting these in right now, okay? I'm going to put the signs in just a second. And then I2 little r. And that has to equal 0, okay? Now as you go through these, this is in the same this is in the direction it's supposed to be going, so it's going opposite that, so it's a negative or positive. The next one is the same, so it's a positive. You're going from the wrong direction on the battery, so it's a negative. And then lastly, again, you're going in the opposite direction of the current, so it's a positive. Okay? And make sure you understand the direction you're going in when you write down A, B, C, blah, blah, blah. That's the direction they want you to do. And so that's how you end up with this. Okay? Now, the second question, number 33, verify the second equation in example 21.5 by substituting the values found in current for I1 and I2. So you go to that and you find the values, okay? So you start out, you go down to the last and you see what the numbers for I1 and I2 are. And the number for I1 is minus 3.5. or I2, excuse me. And the value for I1 is 4.75. So if you put minus 3 times minus 3.5 plus 18 minus 6 times 4.75, and that needs to equal 0. And if you do the math here, indeed it does equal to 0. Okay, number 36. Number 36 is the same kind of problem. Apply the loop rule to A, B, C, D, E, F, G, H, I, J, A in the diagram above. So now let's walk around. First you have, and I'm going to start out without signs first. I1, R1, E, I1, little r1, I1, R5, I3, little r4, E4, I3, little r3, E3, then I3, R3, and then all of that has to equal 0. I didn't say that these didn't get complicated sometimes. Okay, so with I3, I1, R1, in the direction that we're going, we're doing the same direction as the current, so that's a negative. E1, we're going from negative to positive on the battery, so that's plus. I1 little r1 is also in the same direction as current, so that's a negative. I1 r5 is in the same direction, so that's a negative. I3 little r4 is in the same direction, so that's a negative. E4 goes from positive to negative, and therefore it's negative. Then I3 little r3 is negative. It's in the same direction as the current. E3 is from positive to negative, so it's positive. I3 little r or I3 r3 is in the same direction as the current, so it's negative. And so that's the signs, okay? And the nice thing here is most of the time with these equations, you end up with 2 equations and 2 unknowns, and and then it's just math. And the math is actually pretty challenging in these problems. I'm not going to lie to you. So I try to keep it pretty simple when I do a quiz or a test on these problems. Number 44. Now number 44 moves into a different area. It's the area of DC voltmeters, direct current voltmeters, and amp meters. Okay. So number 44 states, find the resistance that must be placed in series with the 25 ohm galvanometer having a 50 microamp sensitivity, the same used as discussed in the text, to allow it to be used as a voltmeter with a 0.1 volt full scale reading. So little r in this is 25 ohms. V is 0.1, and I is equal to 50 microamps. Now the RT, which is what we're trying to find, is going to equal, big R plus little r. RT is equal to big R plus little r. Now this, substituting V over I plus little r, gives you this equation, and then you put the numbers in. So you get 0.1 over 5 times 10 to the minus 5 plus 25. And if you do the calculation, then RT equals 1975 ohms. Okay? Okay, so now 46, instead of a voltmeter, we're looking at an amp meter. And instead of in parallel series, we're looking at parallel. Find the resistance that must be placed in parallel with a 25 ohm galvanometer and a 50 microamp sensitivity to allow it to be used as an amp meter with a 10 amp full scale. So IR here is equal to the I for the galvanometer times little r. So if we rearrange this and solve for this, which is what they asked for, then that's going to equal R times IG over I. And then if we put the numbers in, 25 times 5 times 10 to the minus 5 over 10. And that equals 1.25 times 10 to the minus 4 ohms. Number 58, excuse me. Now number 58 starts another section, and this is a section called null measurements. And null measurements mean measurements that are done if there is no movement or resistance movement, okay? And it says calculate the EMF X of a dry cell for which a potentiometer is balanced. That means that there's no current movement when Rx is 1.2 ohms, while the alkaline standard cell with an EMF of 1.6, the Rs is 1.247. Okay, so Ex is equal to I times Rx, this Ohm's law again. Es is equal to I times Rs, S being standard and X is being the unknown. And you can get this from figure 2135 in the book. So if you put Ex over Es, you get that that's going to equal Ix over Is, which is equal to Rx over Rs. Okay? And therefore, if you take this equality and solve for Ex, Ex is going to equal to Es times Rx over Rs. And then you put the numbers in. 1.6, Rx was 1.2, and Rs was 1.247. And so that gives you 1.54 volts. 60. 60 says, to what value must you adjust R3 to balance a Wheatstone bridge if the unknown resistance Rx is 100 ohms, R1 is 50, and R2 is 175? Again, I'll refer you to figure 2137, which is where they work through this in another problem. Rx is equal to R3 times R2 over R1. And again, look in the book at this thing and it'll show you, I can't draw that figure, so I'm going to leave it like that. Now if we rearrange this and solve this for R3, R3 is going to be equal to Rx times, and this turns it over, it's R1 over R2. And that's just math, okay? And so that means that it's 100, which is what Rx is, times 50, which is R1, and R2 is 175. And so R3 has to be 28.6 ohms. 64. A heart pacemaker fires 72 times. Now we're in something called DC circuits containing resistances and capacitors, okay? A heart fires 72 times a minute. Each time a 25 nanofarad capacitor is charged by a battery in series with a resistance to 0.632 of its full voltage. What is the value of the resistance? Okay, for these problems, there's something called tau. And I'm blanking right now on what tau is. I think it's something called the time dissipation constant or something like that. But anyway, it's equal to 60 seconds and it fires 72 times, so each time it fires every 0.833 seconds. Now tau also equals the resistance times the capacitance. So that means the resistance is equal to tau over the capacitance, which is 0.833 divided by 2.5 times 10 to the minus 8. And so the resistance is 3.33 times 10 to the minus or plus 7. A 500 ohm resistor, an uncharged 1.5 microfarad capacitor, and a 6.16 EMF are connected in series. What is the initial current? Okay, the initial current for this, I is equal to V over R, Ohm's law, and so this is going to be 6.16 divided by 500, or 1.23 times 10 to the minus 2 amps. So that's the initial current. Now, these things decay at a certain rate. And so B says, what is the RC time constant? So the RC time constant is tau. And so that's going to be equal to 500 times the capacitance, which is 1.5 times 10 to the minus 6. And that number is 7.5 times 10 to the minus 4 seconds. C says, what is the current after one time constant? Well, one time constant causes a decrease of EMF, so V decreases the EMF by 0.632. I'll refer you back to there's a part in the book about this. And that's going to be 6.16, which was the initial voltage, times 0.632. And so you end up with 3.849 volts. And then the current then is equal to E minus V over R, which is equal to 6.16 minus 3.894 divided by R, which is 500. And so the new current is 4.53 times 10 to the minus 3 amps. And then the last question on this one says, what is the voltage on the capacitor after one time constant? Well, we already calculated it. It's right here, 3.89. I'm going to skip or defer the last problem. I don't think it's relevant or we need to do that, and stop at this point.